All right, well, let's get started. Thank you everyone for coming to the Digital Forestry Digital Ag Seminar Series. And today we are very lucky to have a guest speaker, Dr. Joe Mascaro. Joe is currently the director for science program at Planet. And just a little bit background about him. He's an undergrad degree from University of Michigan, and then went on to his PhD at University of Wisconsin, Milwaukee. After that, he was a postdoc at the Carnegie Institute for Science, I think, and also was one of the fellows with AAS. So with that, he will give us an overview about what the Planet Lab and how the capacity and how we can tap into it. Welcome.
Thanks, Tom. Thanks, everybody. I'm going to stand over here so I can advance the slides, and I think so you can hear me online. First, thanks to Sunlin and Jennifer and Nancy for helping me with this visit to Purdue today. It's really exciting for me to be here. I've been to most of the Big Ten schools, you know, the schools that Michigan is the champion of over the last few years, but I've never been to Purdue, so it's been great to be here and learn about campus this morning, and I have some more meetings later in the day. I want to talk about global change, and I wanted to take us away from satellite imagery and Planet for a moment. So this is a photograph I took at a place called Ashfall in Nebraska. Has anyone been here, actually? It's not that far away. It's about 3 hours, I want to say, north of Lincoln, Nebraska. So if you have the family and you're going cross country, it's definitely worth stopping. It's a Miocene fossil site. It's about 12 million years old. And the center character there is a North American rhinoceros. There are roughly 150, and they're still finding more fossils at this site. They were all killed over the course of probably a few days, maybe a week, when a super volcano eruption just buried the middle of the country, such as it was, in ash. And back then, you know, North America was sort of a warm tropical savanna. And I just like this because it kind of puts things in perspective a little bit. We're facing a climate change crisis. We're facing a biodiversity crisis. But for other life forms on planet Earth, things have gone considerably worse. And I think we still have a lot of work we can do to attack these problems and move forward together. There's another example that I think is really important as it relates to multidisciplinarity. And I know this slide doesn't look like multidisciplinarity, but hang on for a moment. So this is a stomate on a tomato plant. So for those of you not doing plant physiology and things, stomates are the cells where the plants have a pore that they open to exchange gases with the atmosphere. What I think is really cool about this is that it is here where the CO2 concentration in the atmosphere is really, if you will, hitting plants where they live. Their sensitivity to CO2 concentration kind of happens along this border. And something happened a little bit before those North American rhinoceroses died out, which is that Earth's carbon dioxide concentrations were actually declining. And now we're looking at something like 30 million years ago. CO2 began to decline. It went through a long, slow decline, and it maybe got down as low as something like 150 parts per million. That's quite a bit lower than it was during the Industrial Revolution. And that's at a level that's low enough that it stresses plants in terms of being able to acquire enough CO2. And something happened around this time, which is that plants innovated. They evolved, and many of them kind of, if you will, spare the oversimplification, solved this problem. This is when C4 as a photosynthetic pathway appeared. This is what corn uses. And also when CAM appeared, the cruciulean acid metabolism. And in what I think is like, these are C4 example, I think this is Schizocarium, and here's of course some succulents that you might have in your house. So these use C4 and the CAM photosynthetic pathway. They account for, I think, roughly 5% of plant species total at the most, but an enormous amount of plant biomass on planet Earth, and including especially in agriculture with corn. What I find fascinating about this is the way that this innovation occurred. This is a sort of cladogram of where you see C4 and CAM. We now know that it evolved, combined, they evolved these two pathways more than 100 times total separately. This is one of the most elegant and dramatic examples of convergent evolution in the whole biosphere. So faced with a common global stressor, the metabolism of photosynthesis itself evolved, and these two innovations appeared as like copies of each other, but they were invented, if you will, independently by plants. And of course, this process took several million years. I think we're kind of in a similar situation. We need new operational systems to understand our changing planet. But the nice thing is that we're not bound by the limits of natural selection at the level of the individual organism, because we can do things like we're doing today, which is share information and collaborate. So I'm really here at Purdue to figure out how we could think about doing some things along those lines in terms of collaboration. I want to go through the different levels of organization that we think about climate change, and I will talk about planet throughout much of this, but a lot of what I'm going to talk about is more general than that. It reflects a revolution in global remote sensing that's driven by some underlying trends. Here is one of the most important trends. This could be exciting. Let's see if I can. I think I can click this one. All right, the first audible of our match. Okay, here it comes again. Let's try if I do dismiss all. Sounds like some software updates are in order. We talked about CO2 declining, of course, right now, in the Miocene, but right now our CO2 concentrations are going up. We're roughly 415, 420 parts per million. That sawtooth, I'm sure many of you know, is the sort of annual oscillation of the temperate northern hemisphere part of the biosphere. But you can see this steady increase, this increase on the right, happening a little bit later, but very much happening in earnest now, is changes in the launch of space operating remote sensing observation satellites. We are in the midst of an industry-wide explosive growth in getting payload from the Earth to orbit. And this has dramatically reduced the cost to getting an Earth observation satellite or a communication satellite operational. There are many examples of this. I'm sure a lot of you have seen the Falcon 9 SpaceX vehicle not only flying to space, but turning around a portion of it, the first stage, and coming back and landing at several of their landing sites around the Earth. So we're playing a little bit of catch up, but we now have an industry that's scaling up that is positioned to begin to collect and is collecting just a skyrocketing amount of observational data about the state of our planet. And that's really phenomenal. There are also new kinds of capabilities. This is one such capability that Planet has. Other providers are doing this capability as well. This is high resolution panchromatic full motion video from orbit. This is collected by a SkySat, which is about the size of a dishwasher. Planet operates 21 of these spacecraft today. And this is a few days before, actually a month and a half, I think, before the successful launch of Artemis, but that's the Artemis moon rocket on the launch pad at Cape Canaveral. So our mission as a company is to image the whole world and make change visible, accessible, and actionable. We operate over 200 satellites. More than 200 of those are Dove CubeSats. They are about the size of a football or a loaf of bread. They're 10 by 10 centimeters by 30 centimeters deep. Then they have the solar panels that extend outward. And then the SkySat high resolution constellation I mentioned images at 50 centimeters per pixel at nadir. Those are tasking satellites that we actually just swing and point to a target to collect it. This is what the whole system kind of looks like in operation. So we're watching the Earth rotate to the east, and this strand of small satellites coming down from the north to the south, like driving a Zamboni or mowing your lawn, is a constellation of these dove CubeSats. And they're about a minute behind one another in orbit. It's a 90-minute orbit, so there's 100 is what you need to get you to daily imaging, and we have multiple orbits of that. So we're collecting strip after strip after strip of data. And then these ones coming in this more inclined orbit, the SkySats are in a mix of different orbits. Some of them are in the same north to south sun-synchronous orbit, which is similar to Landsat and Sentinel, but some of them are operating in an inclined orbit. And this allows us to shoot the same target multiple times per day. And then we are trying to put these observations together in order to gather more information about the Earth in a synergistic way, a way that leverages the trade-offs between these different types of instruments. This is very similar to deploying, for example, terrestrial sensors like LiDAR sensors on cars, UAV sensors on drones, and satellite data into a constellation of data feeding into a particular project. This is an example of detecting change, and in this case, a relatively simplistic but important detection of change. This is a fast military bridge that was placed over a river in Ukraine during a time when Russian invasion forces were moving into Ukraine. And you can see that this was detected, this says February 14th, and then February 15th is what it says under here. So detected just in that daily frequency. That's with the Dove CubeSat, but then with the SkySat constellation, we can look closer and understand things in a more granular way. And this was around the same time frame, the buildup of Russian military forces along their own border in Russia over the course of several months. Planet is not operating in a vacuum. So these spacecraft and their data feeds are producing data that is collaborative with a massive and increasing government-sponsored Earth observation campaign. I'm sure I'm looking at a room full of people who are consuming and using data from many of these NASA sensors. Then, of course, we also have the recent ESA fleet, particularly the Sentinel program, which has resulted in a skyrocketing amount of analysis of the changing Earth surface. Okay, so that's the measurements. That's taking pictures, collecting data, collecting input information. I want to talk about discovery as the next phase. And this is really why I'm here. And for me personally, this is, I think, what I get most excited about in my work. Just this morning, I met some people whose names I knew because I had read their papers or seen their papers before, but I'd never met them in person, and that's really exciting. We are operating multiple different science programs. The biggest of those is called the Education and Research Program. It's a university program. We have more than 20,000 users in the program globally, and with more than 100 universities that have site licenses with Planet or strategic partnerships. This is similar to how Esri, Microsoft, Adobe relate to universities. We're also in the process of trying to improve and increase the equity of this program. So what you're looking at is a map of where these users are at the country level in blue. And then also these individual site licenses are the dots. The ones in red are universities that have campus-wide access, so all of the people on campus can access large volumes of Planet data to do science. But as you can see, there's a healthy bias here toward North America and Europe, which I think is mostly an accident of Planet's origin and its existence and its acquisition of a European company. But we're working to expand this globally, and it's something I'll be focused on heavily for the next several years. We also have additional partnerships. I know some of you are leveraging these already with NASA and with the European Space Agency and with the German Space Agency, DLR. So I've already promised to send some details to Sun Lin about how to get access through one or more of these programs, and I'll make sure to do that and route you to the right place. But let me talk about what people are understanding and discovering in the data. And I'll do a quick tour for a few minutes, and then I really want to spend some time talking about phenology at the tree crown level. It's something Sun Lin and I have been talking about over the phone. And I'll actually start there just with a preview of it, but I'll show a few more of these in depth. So on the left is a study out of UC Davis. It's one of several. This is a lab led by Yufeng Jin, who's a professor there. and they study almond production among many other things. And what they're looking at is the behavior of the flowers on almond trees, which are correlated with almond yields. And in this case, the fact that planet images at such a high frequency allows them to capture those flowering events. And they're doing that with a thing called the Enhanced Bloom Index. It's not that different from NDVI, but it focuses on the flowers. In this case, they're white flowers. So they look for a spike in that EBI and perhaps a reduction in greenness, and they're able to make estimates of almond yield. There's a completely different group in Western Australia, and actually the guy who led this work, his name is Dan Dixon. He's now working with UFang. He's taken a postdoc at Davis. But he applied this same kind of indexing to look for flowers on a eucalyptus species in southwestern Australia. And you can actually see here on one of these figures, you have this reduction in greenness and a simultaneous increase in the EBI, the Enhanced Bloom Index. But this allowed him to isolate a particular eucalyptus species in a conservation area. Being a forest ecologist myself, I know that the use of flowers in this part of the world is probably, there might be some examples where this could be used. I'm thinking of things like redbud or magnolia trees. I want to be careful to set expectations that I think detecting sugar maple flowering events versus silver maple flowering events, probably not at the level of our technology yet, but it's a pretty cool idea. Getting really excited. We get really kicked out of here. No, we don't do that.
Yeah, I don't know why
Right.
it's doing.
It's okay. My machine does that too. It just yells at me at all times. These two, from two completely separate labs, look at air quality. This was interesting to me because the Planet CubeSats were designed to be a land surface monitoring mission. So the spectral payload on board the spacecraft deals primarily, it's most sensitive to RGB, what humans see with their naked eye, but also vegetation. We started with a near infrared band, and we now have 8 spectral channels across the visible to near infrared. The point being that the instrument was not designed to look at the atmosphere. If you're going to build an atmospheric sensitive spectrometer, you probably would build it differently. But we do see, like any visible sensor, the occlusion of the atmosphere by clouds and haze and other atmospheric phenomena. And in this case, a lab at Duke and then another one in Sweden used our data to estimate PM 2.5. And they were then able to make spatial maps of the PM 2.5 estimated concentration in the atmosphere by co-registering our imagery with ground-based air quality sensors that were directly measuring PM 2.5. So they basically are doing a spatial model that is, it's certainly not simple to make, but it is, I think, simple, elegant to understand, right? Where they have these very highly sensitive points, and then they have the less sensitive planet information kind of draped over the top of it. That's going to be a constant theme of everything I show you, and I think something I'm eager to talk about with you all. In a completely different ecosystem and with a completely different applied challenge, two, again, totally separate labs, no authors in common, are using Planet's CubeSat data to look at water turbidity. And again, here, the instrument was not designed to study the water. However, it's sensitive to water turbidity in the ways that a visible near infrared sensor tends to be. And we do get pretty good water penetration down to maybe 12, 13 meters depth. So there's a coral mapping group at Arizona State University. This is a lab led by my former postdoc advisor. And they're using the high frequency data. In this case, they analyzed thousands of images in Hawaii to understand changes in turbidity over very high frequency daily events. So they can see how rainfall and plumes into the marine environment around Hawaii affect the turbidity on the fly. This one is really striking. This is from a university in Italy. Similarly, apply the Dove CubeSats to look at turbidity, in this case in Venice. And the relatively high turbidity on the left here is the weeks leading up to the COVID pandemic and the initial lockdowns. And the ones in blue are the first few weeks at the most extreme level of global lockdowns. So what was going on is that Venice harbor traffic had dropped drastically, and the water clarified itself as all of this sediment that churns around the Venice harbor just fell out of suspension to the ground. It's kind of amazing. That last one gives a preview, I think, of thinking about this climate change problem as a global problem. We're starting now, we're now we're a little bit away from just remote sensing science, and we're into social science. How does the COVID lockdown affect the Venice Harbor water turbidity? It's more than just an Earth systems question. And there are many other examples of this kind of application of the high frequency data. The one on the left is another COVID example, and another one that I think stretched what we maybe initially thought was possible with the Dove CubeSats. They image at 3.7 meters per pixel. So that means one pixel could hold, an F-150, right? But these authors were able to detect the relative abundance of vehicle traffic on open roads in urban centers because of the high frequency time series. So on certain days, the freeways are packed with cars, and that has a different spectral signal, the parking lots too. And on other days, the roads were more clear, and that has a different spectral signal closer to pavement. So even though they couldn't find individual vehicles, they could detect the relative abundance of vehicle traffic. And sorry to step in front of this, but this blue line here is the reduction in traffic that's detected in planet data, the trough there, and the red line is the relative strength of the lockdown at those locations, again, a post-COVID detection. Another example, kind of the same idea, except in this case, looking at open markets in Ethiopia, Kenya, Uganda. And although not a complete shutdown of those markets, what they did was calibrate with very high resolution imagery to find open street markets, and then look back at those same locations in the high frequency data at the 3.7 meter resolution, and found that market frequency had declined dramatically during the lockdown. Along the same lines, poverty mapping in London, in this case using Google Street View. Down here in Malawi, this is maps related to cell phone abundance. Notice that all of these studies are taking some kind of localized observation. It might be very high resolution, hand labeled street markets, or it might be some kind of cell phone data, that's cell phone location data, but it's some kind of non-satellite data, right? And intersecting it with the satellite data over time in order to make spatial models and maps of patterns over time. Okay, we're getting now into things we really did design the system to do. So I want to talk about remote sensing itself, and then also a little bit about, as I said, phenology and a few other vegetation applications, which it's really quite excellent at. So all four of the studies highlighted here are kind of core remote sensing science studies. Each one of them is attempting to stabilize the radiometric signal from a diversity of different satellites. So I'm sure there's people in the room dealing with this challenge. If you put Landsat data in a time series with Sentinel data, you have a challenge, right? The pixel size is different. The radiometric architecture, although similar, is different. The band passes are different. The frequency of observations is different. And even within one sensor, like Sentinel-2A, you have some pixels in certain channels that are 10 meter, some that are 20. So it's almost like you're building this big Jenga tower of observations over time, right? Where it's fundamentally always kind of heterogeneous. All of these authors, all using different widgets, if you will, different modeling techniques. They all tackled the same challenge, but with using planet data plus some other public sensors. The first one, and the lead author of this, Rasmus Hoberg, is now a Planet employee. He leads a fusion team. He's our senior fusion engineer. Worked on at King Abdullah University of Science and Technology. What they did was intersect multiple planet images over time with the full Sentinel record, the full Landsat record, and the full MODIS record of the same area. So truly like assembling a Jenga tower. And then use QBIS regression to create almost like a clone of the same time series, where they're able to spit out estimated, statistically inferred surface reflectance values for every pixel at planet resolution for every single calendar day. So they can read in this huge Jenga tower, and what they spit out is 365 days of continuous 3.7 meter resolution reflectance estimates that reflect the consensus of all those public sensors. This is quite transformational in my view, and rather different than the way we would think about, say, doing an NDVI time series off of just Landsat 5, right, where it's one sensor and you can kind of plug and play. And without going through all the details, because they are fundamentally similar in the way that they applied this kind of methodology. Jin Wu's lab, this is work out of the University of Hong Kong. I'll talk more about that when I talk about phenology in a moment. This is the Liège University in Belgium. In this case, going so far as to put out estimated 3.7 meter resolution shortwave infrared. So this is interesting. Now they're taking a spectral channel observed by Sentinel-2, but not observed by Planet, and they're using the same style of spectral temporal fusion methodology to generate an estimated shortwave infrared value at Planet resolution. I think, frankly, I mean, this work needs additional validation and replication from other labs, but you can understand why it would be somewhat useful, and of course not the same thing as measuring shortwave infrared directly. There's other studies that have tried to do this with thermal. And the one on the left is University of Illinois, just up west of here. Looking in this case at leaf area index, but the same basic idea. They really rely on the Landsat-based leaf area estimator, and in this case, they drink in the Planet data and the other sensor data collectively as well. Okay, I'm not going to go through all of these, but these are all above ground carbon stock spatial modeling and mapping exercises from labs all over the world. Most of these labs are independent from one another. I will mention one because they have another paper out very recently in Nature a couple of weeks ago, using our SkySat constellation. But this is work out of the lab run by Martin Brandt at University of Copenhagen. So they've collaborated for years with Jim Tucker at NASA. They're mostly focused on carbon landscapes in Africa, but especially arid treescapes, these ecosystems like the Sahel, where most of the carbon is in really sparse trees. Every single one of these papers, though, every single one, is some kind of hard to get local scale data set like a field plot or plot network plus UAVs maybe, or ground sensors like terrestrial LiDAR, and then large scale data sets with hand labeled data or some kind of spectral radiance correlation that's built, or textural correlation that's built through a spatial model with the underlying Planet data. But in all of these cases, what you're really doing is stacking data in space and time and writing spatial models to get those two data layers or multiple data layers to talk to each other. This is the part where I say I would have made one of these with agriculture stuff on it, but it would have covered up the whole map of the world. And I think at this point, you understand where I'm going. Okay, let me talk about phenology, and I'll just spend maybe 5, at most 10 minutes on this, but I did want to talk about it because I know it's paramount for the way Song Lin is looking at things and the rest of the digital forestry group. I think this is one of the areas where Planet's data set, where the pixels are generally smaller than a large tree crown, at least in temperate and tropical forests, not quite as much true in boreal forests. But for the most part, that 3.7 meter pixel, if it falls on a large oak tree on Purdue's campus, you're going to get a pixel, maybe a few pixels on that one crown. And that's a step change. That's different than Sentinel-2 and especially Landsat, where in the case of Landsat, multiple trees are kind of smushed together in a single pixel. So here's an example. This is Guayacanas trees on BCI, Barro Colorado Island in the Panama Canal. This is Smithsonian Tropical Research Institute site where there's a forest geo plot. This side of the island over here, where there's more of these yellow dots, is actually secondary forest, which is partly why Guayacanas is a little more abundant here. But this happens for about a week or 2 weeks. The Guayacanas trees are deciduous. They drop all their leaves. They flower spectacularly across the whole crown, and then they drop the flowers. My point is that this is a rare temporally and difficult to see spatially phenomenon, like phenological event. And if you watch the whole canopy through like an animation, you can actually see the crowns going through this deciduousness behavior and flushing behavior at the level of the individual crowns. This is in the Dove imagery, so we haven't even gotten to the SkySat imagery yet. Okay, since I think a lot of you know this stuff already, I want to breeze through this one slide and just talk about phenology in general. How many of you have seen images like this? So this is an RGB image. where red, let's see, this is not Planet Data, Brooks et al. 2020. Red is the phenological seasonality, so sort of wavelength, if you will, of the greenness changes in the vegetation or the pixel, productivity, and timing. What's happening is that I like to think about it like you imagine one pixel changing over time, and you're taking a derivative or a moment of inertia of certain kinds of events off that pixel. So days when flushing occurs at that one pixel are really highlighted here. And what this figure is meant to show is similarity. So that means if it's yellow, then the days of flushing are likely corresponding or coinciding with one another. Whereas if you see yellow and red, the days of flushing are going to be farther apart on the calendar. This kind of analysis style is something that people are increasingly applying to planet data. And where I'm headed here is one that's done at the level of the individual tree crowns. But first, let's look at just a land cover analysis example. This is work out of Boston University, Min-Kyu Moon. It's a postdoc there with Mark Friedel. So what's being mapped here is one of these phenological timing events. We have here a true color planet image, so just a regular surface reflectance image. But then this figure in panel B is the day of the highest enhanced vegetation index amplitude. So I think of it like this is the day, calendar day of the year when the greenness is accelerating the fastest, right? And so this is actually a figure where every pixel is the Julian day. Like they have values like 172, 128. This is phenomenally interesting because you can see that it's like a potential ingredient to, say, a classification map if you care about land cover, or a habitat map if you care about ecosystem services. But it's not at the point of that classification yet. It's almost like you've given a environmental variable or a parameter that you could feed into a subsequent analysis. And so the lab at Hong Kong is doing the same thing, and they have a few papers that have looked at this for neon sites in temperate North America and one in temperate forests in northern China. This is one of the examples from the neon sites. So this is high-resolution drone photography here, and they have these phenological transects around the neon areas where they are looking at field-identified tree crowns. And they're doing the same kind of thing we described with the Julian day. So they take the phenological variation throughout the calendar year, they're decomposing this using derivatives to these events. Start of spring, end of spring, middle of spring, start of fall, end of fall, middle of fall. And what they argue is they have some leverage, this is early work, but they have some leverage where the species of the tree is a sensitive, is detectable because of the relative differences in the timing of these particular events. In other words, I think of it like, the oaks might leaf out a few days after the elm trees or the maple trees, or vice versa, right? So they're arguing this at the genus level in most cases. Here's another kind of just schematic of how this works. But here's the same lab work in China and same style of analysis. So now, like the Moon paper, they took those phenological events and mapped them back to the individual raster pixels. This is a forest inventory plot, start of fall, middle of fall, end of fall, and again, they're showing the Julian day. So in red, these are trees that held on to their last few brown yellow leaves the longest. They didn't drop until late in the year, like December. These are trees where those leaves dropped at the end of fall earlier. Right? And they're using this as a discriminator when up here on the top, they show some weak, but some leverage to distinguish individual temperate tree species. This is, I think, really exceptional work. This is the last example, but again, from a different lab. And usually now, I read the literature, admittedly, at a shallower level than I did when I was a PhD or postdoc, because I have to kind of scan the whole thing and try to find what's important and urgent and who to talk to. But when I see multiple labs working on similar pathways, have no co-authors in common whatsoever, that looks like a significant shift in the way that the community is thinking about this data. And that's what's happening with Planet data as it relates to phenology. This is another lab from Belgium, no authors in common with Hong Kong, the Hong Kong group or the Boston group. But again, they're doing the same thing. They take first these, actually this might be a habitat map in this case, but here, what they've done is at the pixel level, based on the phenological timing of decomposing those moments of inertia, they are doing a cluster analysis where they're showing the relative fraction of these, at the pixel level, relative fraction of the abundance of beech trees or spruce trees or oak trees. And here they put all of them together in RGB. So they show the clustering around, like the green is most likely, most probably a beech tree. The red most probably oaks. Okay, talked about Dan Dixon already. So let me move on. In fact, actually, the phenology thing was a bit wonky. So I could take, if we want to, I'm happy to take a question about that at this moment. I have a few more sections I want to go through, but I don't want to. Okay, let me continue. All of those analyses were done at the level of an individual lab, and usually in a small localized area, right? We're talking about some neon sites. In the case of the fusion work, we're usually talking about a few agricultural sites. But we're increasingly seeing, and we're really encouraging, and I think we'd love to work with Purdue on larger scale, much more applied projects that have a real big global impact. That's how we're going to take on things like climate change. This is work out of Clark University with collaborators in Kenya and Ghana. And it is the first sort of whole country high resolution assessment of field boundaries. And this was done in part by looking at wet season and dry season phenological dynamics, but especially by tracing field boundaries and then writing a neural network basically to make predictions based on where field boundaries were. But production of a really large agricultural map of Ghana. Similarly, at the national scale, forest carbon. And this is work led by Greg Ausner and several postdocs at Arizona State University. Airborne LiDAR in the bottom right, attached to planet high-resolution, high-frequency data through a spatial modeling routine, and the result being a generation of a countrywide carbon assessment map. This is probably the highest quality national map that exists for the tropics right now, but people are making maps all the time, and I suspect we'll see another set of really great ones as the JEDI data from the space station becomes really more widely used. Doing the large scale analysis, again, still isn't the whole picture. So I want to end by showing you just a few examples of where we're having, through partnerships, I think a much wider impact on how people live their lives and how we protect the sustainability of our planet. And this is what Planet, the company, was really founded to do. This is exceptional work led by NASA Harvest, numerous agricultural scientists at NASA Harvest and University of Maryland. Collaborating with Planet, we provide mosaics and look at how agricultural dynamics in Ukraine, this slide is several months old, so these territorial areas are clearly out of date. But what you're seeing is agricultural production. And the really interesting thing, so this is now just true color, but for Ukraine as a whole, if you try to avoid looking at the line, you'll just notice these darker patches here in the ag system that kind of trace along this line. Those are fields that were not harvested. So they were planted, grown, and then just not harvested at the end of the season. This is like a ecological signal of the presence of the front line in this war. And then the line itself is drawn on the map there. There's really a remarkable kind of correspondence between the conflict itself and the ecosystem behavior underneath. Another challenge, although a natural one more so, is the proliferation of wildfire in the state of California. This is a tool led by Salo Sciences, which has recently become part of the Planet. And here, like many of the spatial models we looked at earlier, they're intersecting LiDAR data, airborne LiDAR data, which is heterogeneous, but it's patchy collections of LiDAR throughout the state of California, with statewide mosaics. We take all the CubeSat data together and chop them up in little temporal bits like monthly. And then we're able to see the do modeling between the LiDAR, just like in the Peru example, between the LiDAR and the satellite data in order to make carbon maps. And this is integrated with information on wind speed. So you can do fire modeling in here. It's called the Forest Observatory. And you can still find this. It's at forestobservatory.com. Through additional partnerships between SALO and upstream tech, we're also thinking about this in terms of understanding carbon offsets or carbon management. This is an example of a tool. This is upstream tech's tool where you can take one of the outputs of these SALO spatial models and do a time series analysis where you can look at carbon acquisition over time. And the idea here is that with improvements in accuracy and uncertainty modeling, you could begin to assess individual pieces of property, say through a carbon mitigation project, and then ascertain how that project is accumulating or losing carbon over time. We have a large partnership with the government of Norway that's serving our high-resolution mosaics for tropical countries. There's more than 2,000 users leveraging this data. This is another of the programs I wanted to mention if you're interested or studying tropical ecosystems. The use of this data is quite easy, and so we can get that to you. And a project in correlation with Arizona State University collaboration, with Arizona State University, the Coral Reef Alliance, University of Queensland. This is the Allen Coral Atlas. Yet another spatial modeling exercise. We take localized field observations and put them together with the satellite data in order to look at habitat analysis for coral reefs. I'm going to skip this slide and say I'm just going to cover these last few. So this is a kind of framework for how we think about putting together a diversity of observations from multiple sensors, but doing so in such a way where you can produce a derived product or an applied product that can actually drive decision making. So this kind of hourglass figure, what you have are sensor inputs, usually at relatively low levels or more granular levels, radiance data, reflectance data. But in this case, centered around some kind of fused level 3 product. When I talked about that Jenga tower and generating a copy of it, where you basically are writing out the estimated reflectance, that's one example of a tool that would allow you to do that. And then you're building, say, UN SDG monitoring tools or carbon map, carbon project offset mitigation, reinsurance, et cetera, products. But you're doing so in a way that's centered around common standards of openness and radiometric calibration and the fusion of surface reflectance data. So if we take the work that we looked at from Peru, that work would fit this kind of framework where we have some LiDAR data that's close to the sensor, it's measurement data. We have Landsat Sentinel Planet, pretty close to sensor, but it's been processed maybe up to level 2. We're putting that data together and fusing it in some kind of common spatial infrastructure, like STAC is one of the tools people use. So that when you're generating a biomass map, your tool in the future over time can read incoming future data from these sensors. You could acquire new LiDAR data sets and just drop them into this functional tool moving forward. And this is the kind of thing that SALO has built for California. But you could just as easily take the similar engine and apply it to some kind of different problem. In this case, I mapped it out for UN SDG 1, which relates to wealth or poverty mapping. I'm going to skip this. Okay, so I just got a couple of slides to talk about future upcoming capabilities. I mentioned our current constellation at the beginning of this. We have 2 satellites forthcoming. They're both expected to launch this year. The first one of these is called Pelican. It's a follow-on to the SkySat high-resolution mission. So these are satellites that we're going to point and task and collect from individual fixed targets similar to SkySat. And the one I think scientifically we're really excited about is called Tanager. This is a hyperspectral mission. It's a spectrometer built in collaboration with JPL and a nonprofit called Carbon Mapper with 420 spectral channels at 30-meter resolution. The first mission for this instrument will be to look at methane emissions. So there's a critical need right now to understand, say, smokestack emissions that are not flared, where basically the gas flare has gone out and you're just pouring methane into the atmosphere. But it has really exceptional potential applications for all kinds of other areas. not going to go through all these. I think the one I'm personally most excited about is biodiversity. So although at 30 meters per pixel, it will be, yeah. What I have? Oh yeah, another one. Now I'm just going too fast. I can't even see them all. I'm sure. I'm not sure. They're not mine. I think with the hyperspectral data, I'm sure a lot of you have worked with hyperspectral very up close to target, where you can see the leaves even or the tree architecture. So this will be a bit of a challenge of taking these 30-meter hyperspectral spatial observations and trying to intersect them with the other high frequency observations or potentially ground-based observations. But I think it does paint a picture where we'll increasingly be able to monitor and identify particular tree species and ecosystem types. So this is kind of the whole picture right now. I want to end there. I feel like I can feel myself like overheating over here. That's probably I'm talking so much or so fast that I've like warmed up the room. But why don't we pause here? I'd be happy to take any kinds of questions you have. And yes, this is your own athletic facilities taken from SkySat, I think just a few months ago before it got gray around here. But thanks again for having me.
Open question. We have a file submitted.
Yep.
So for a company that kind of prides itself on not only spatial resolution but temporal resolution, right? How is Planet tackling the data access issue in terms of like, I would say we spend significant amounts of time on data discovery, download, unzip, pre-process, right? Just to get to a period or a point where we can actually start doing analysis. And when we start talking about that on a countrywide or regional or global scale, you're pretty exponential in terms of time consideration.
Yeah.
So, what tools are you all developing, or what would you recommend that you've seen best practices for dealing with?
Yeah. The first thing I would encourage you to look at, are you using any of the integrations right now, for example, with Esri or Earth Engine?
I know they exist.
Yeah.
I haven't played with them very much, but.
Okay, so, we've adopted an Earth data platform strategy, but we are in the process of building it. I can completely empathize with you. I search for and browse and download planet imagery regularly. I think I've gotten pretty comfortable with finding if I need 1 or 2 or 5 images. That feels pretty straightforward to me. But for example, we visited UCLA not long ago. We were in Kyle Kavanaugh's lab, and they're doing kelp forest analysis all along the California coast. So they have like 6 kilometer wide polygons that track the coastline all the way up, and they need every single planet image in all of those polygons, and every single one of those polygons is like slightly different shapes. The integrations are a first potential place to go, but I think the really critical thing is being able to do bulk ordering and collecting all that data simultaneously in one common storage infrastructure. I will say that when we partner with universities, and also through our partnership with NASA, for example, we have full-time, and they're often credentialed scientists, PhDs in several cases, remote sensing scientists, who are deployed to take on the challenge of, say, a unique download or operational need of a partner. So if, and this is just a hypothetical, actually, let me just point to Kyle's case in this example, is that, basically took one of these professionals to UCLA physically, met with Kyle, met with his whole graduate student lab, understood the nature of the challenge over the course of several hours, and then departed and wrote a script in order to do what Kyle needed to happen. So that's gonna, I think, take some cycles for us to continue to optimize, but it is a really common source of pain, and we certainly hear you, and we want to work with you to make it better. But I would definitely check out the Esri and Earth Engine integrations as a great place to start, depending on what your compute and storage situation is. Yeah. Are you, if I could just ask, through what programmatic mechanism are you using data right now? Through NASA?
So
It's kind of a wide range of various platforms.
Mhm.
Right now.
Okay.
But the typical mode is using embedded data discovery mechanisms, like you said. I need these 10 images. Let me go grab these things.
Yeah.
Let me download
Yeah.
them. Play with them. But as I look at expanding, a certain set of research
Yeah.
into larger
Larger
scales.
scale. Yeah, like Indiana scale.
Yeah. Or even larger than that, and then this becomes a massive problem.
Yeah. No, it's it's non-trivial. Martin Brandt's lab that I showed the arid African ecosystem example, they're downloading hundreds of millions of square kilometers of planet data. So it's hundreds of thousands of images. But they have local storage and compute that they work with, so they sort of prefer to do it that way. But I agree with you. We're on a path toward greater platform capability, and I think without speaking out of turn, analysis without download is kind of the holy grail, or at least a part of the holy grail.
Question.
So in agriculture and forestry, remote sensing, people care a lot about quality or signal over noise.
Yeah.
When we're taking satellite images, the moving clouds, interaction between the Earth's surface, the atmosphere, and the sun angle, causing a lot of variances. So my question is, how well are you calibrating all those noises, and for your current and near future images, what do you think will be the bottleneck noise issue for agriculture and forestry?
So we currently have a radiometric calibration group that works directly with US Geological Survey. One of the things we do for the doves is to leverage many of the same RadCal sites that are used for example, Landsat. I'm actually headed with one of the people that works on this team to the Landsat Science Team meeting in early February next month, and this is our most frequent touch point with USGS is around calibration. We also designed a new form of calibration, at least for input, which is we do lunar imaging periodically with the doves as a calibration ingredient. Primarily, we do that because we don't have a movable, once it's deployed, we never close the shutter again, like the way Landsat will do a closed shutter calibration dark field event. I mentioned, without a doubt, there is a trade-off between, say, Landsat 9, which is an exquisitely radiometric calibrated instrument, and a Dove CubeSat. And the trade-off cuts both ways. So in terms of radiometric uncertainty at the pixel level, the Dove does have higher radiometric uncertainty than Landsat does. However, when you look at signal to noise, for example, it's interesting. If you put the Dove pixels together and you sort of electronically or pixel average them together up to, say, Sentinel resolution, the signal to noise is pretty close to Sentinel-2. Part of the reason the signal to noise is doesn't look as good is because the pixels are sharper, right? So we're collecting fewer photons per pixel. But finally, I would point to this future of sensor fusion. And I think this is going to be really tough. I think this is going to be the biggest challenge for the whole remote sensing science community over the next several years, is the trade-off between continuity and increasing data volume and diversity of sensors with a common analysis-ready data or stack or some kind of common analysis infrastructure that accommodates data of disparate quality, right? We're already kind of doing this. Like if you go to, last time I was an observer at an LST, they had a presentation about the level of effort to calibrate Sentinel-2A and Sentinel-2B. And that's non-trivial. That's full-time people working to get those two sensors into alignment with each other. So this problem is not going to go away. Once you add sensors, you're adding either a novel calibration architecture or you're adding a different uncertainty level associated with pixel characteristics or radiometric characteristics. So I really think that fusion is the right framework to deal with these challenges. but we need to work as a community to figure out what the standards should be on how the fusion algorithm should be run and how uncertainty should be characterized and how version control should be handled. For example, if you have pipelines that are making intermediate, adjusted versions of the data.
So could you give us a very rough quantitative sense of the variance? So let's say we have some beautiful golf course west of the stadium, and let's say we assign the task for all your 200 satellites fleet to repetitively do the sensing at the same location, assuming the grass is not growing or changing. And you collect the 200 repetitive images. What's roughly the variance? 1%, 5%?
It is roughly 5% as of. What I want to do is make sure to encourage you to look at the API product specification documentation. All this documentation is open. You don't even need a Planet account to look at it. So I don't want to preempt the correct answer. My last check-in with it was 5%, but please check out the Planet API documentation and go first, I think, to the product imagery specifications, and you should find your way to a radiometric uncertainty estimate. I will say, we also at times, and I'm just speaking as myself here, we've quoted uncertainties associated with geolocation uncertainty, right? And increasingly, I find these metrics a little bit, how should I put it, a little bit unhelpful, because the more important nature of the uncertainty, in my view, is its heterogeneity. So you just asked about grass growing near, say, Purdue's campus. And that's actually a really important part of the question, because the radiometric uncertainty is not going to be identical across the spectrum, across spectral channels, and it's going to interplay with the actual atmospheric conditions or the nature of the Earth's surface at the particular place. So our uncertainty at the pixel level may be different over, for instance, ice, right? And likewise, our orthorectification uncertainty in Iowa compared to Patagonia, on average, is different because of the way the actual orthorectification algorithm intersects with the imagery content. I will, if I overgeneralize, having worked with now hundreds and hundreds of scientists that have used Planet data, I will say that there's often a notion that the number of satellites sort of changes the dimensionality of the remote sensing problems dramatically or in a qualitative way. I think actually the harder part of that is that the images are on average very small compared to what people have used. I don't know if anyone knows the number, but a Landsat path row is what? Thousands of square kilometers. A Sentinel image is, I think the swath width is 300, 500 kilometers wide. So the average Landsat or Sentinel image is very large. If you look at something like orthorectification, even the same algorithm applied to the same quality data for a relatively smaller image is going to behave differently, because the way it achieves ground lock and the way it's affected by cloud cover is affected by the actual grain, if you will, of those phenomena on the Earth's surface. So, I'm sort of perhaps wandering through this a little bit, but listen, without a doubt, there are trade-offs, and there are some serious challenges when you are working with thousands of images that are only 200 square kilometers. But I would encourage you to continue to try, and we would like to help.
All right, for the interest of time, we'll close. Thank Joe one more time. Question related to Planet, one can access. You may contact Nancy from the conference, send me invitations, and we'll collect these. And thank you, everyone.
Thanks, everybody.
Thank you.